Hello students, I'm going to review question 3 of paper 3, which is probably the most poorly done. So first of all, this question focuses on two elements, namely phosphorus and nickel, and their related compounds as well. So for 3A, we begin by looking at two acids, phosphoric acid and phosphorus acid. The molecular formula is given in the questions over here. So do take note that sometimes when questions are being developed, the molecular formula is given to make your life easier. Yeah, and all these little things or little kind of information sometimes is included in a question really is to speed up your doing process. So please make use of some of these important information in solving the problem. Okay, so molecular formula is given to you. You are being told that phosphoric acid is triprotic, phosphorus acid is diprotic. Although this information is not very useful in the questions, but it's just given to you as a matter of fact. You were also told that the phosphorus center in these oxo acids are sp3 hybridized. A lot of you might not read this part of the question carefully. sp3 hybridized simply means that the shape around the phosphorus center is tetrahedral, and there are 4 sets of sp3 hybrid orbitals, which you should know how to draw from one of your chemical bonding learning outcomes. Okay, so if you want to maybe revise a little bit on drawing of the sp3 hybrid orbital, like what I normally mention in the tutorials, you can actually just use a pencil to just sketch out a tetrahedral shape. Okay, so I don't have a pencil here, and I probably can't do it using a pencil over on screen. So I'll just represent a pencil using a green pen. Okay, so yeah, you just sketch out a tetrahedral shape like this. Okay, so please bear with me for the not so straight line because I'm really just sketching. Okay, and then after that, you can use these pencil sketches, right, to help you position your hybrid orbitals. Of course, this question does not require you to draw all the hybrid orbitals. Okay, so let me emphasize this. This is merely just a revision on how to quickly sketch out the hybrid orbital in a tetrahedral geometry. Okay, so I'm going to just sketch it out like this. Okay, so this is the hybrid orbital. Okay, and then if it's easier for you to draw it vertically, you can always rotate your paper, but I can't rotate the screen right now, so pardon me for the poor drawing. So I'm just going to draw it to the best of my abilities on screen. Okay, like this, okay, and then like this. Okay, so this is the way to draw the 4 sets of sp3 hybrid orbitals. Yep. Okay, so and then after that, if you wish to, you can just erase off the pencil marking if you want your exam scripts to be very aesthetically looking, but if not, you can just leave it as it is, because I think it is quite clear cut that you are actually trying to represent hybrid orbitals. All right, and remember to label your drawing as well. Okay, so in my case here, I did not label it. Okay, so for A part 1, you are being asked, you're being told that both nitrogens and phosphorus are in group 15 of the periodic table. You were asked why similar oxo acids of nitrogen do not exist. Similar here means that why is it that I do not get H3NO4 or H3NO3? Okay, so the reason obviously is due to the fact that nitrogen being in period 2 is not able to expand its octet. I think a lot of you wrote that nitrogen cannot expand its octets. Okay, so if you try to review atomic structure, okay, the electronic configuration for nitrogen is 1s2, 2s2, 2p3. Okay, and then of course that's of phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. Okay, so if you look at the valence shell orbitals, you for principal quantum number 2, you only have S and P as subshells. Yep, so maximum number of electrons that can go into the second principal quantum shell is 8. Yeah, anything beyond 8, I will have to utilize 3s, okay, which is not energetically accessible. Yeah, so that is the main thing which you need to focus on if you wish to elaborate on your answer. Okay, so some of you wrote something like, principal quantum number 2 do not have 2D, or some of you said that 3D is not energetically accessible. But do bear in mind that the next accessible orbitals for nitrogen is 3s and not 3D. Yeah, of course, all these details we do not penalize the students when we are marking the script. But if you want to be really accurate in your answer, you need to know what to focus on, okay? And then for phosphorus, the energetically accessible orbital is 3D. Yep, which is available. So therefore, phosphorus can expand its octet, so-called. Okay, so octet expansion, technically speaking, itself is not a correct way of expressing your answer. Okay, but of course, for 1 mark, I think it's okay. So quite a number of you simply said, nitrogen cannot expand its octet, phosphorus can. Okay, so we'll give you the credit accordingly. Okay, so but do bear in mind that it is important for you to know the full explanation. Okay, so for part 2, many students did not count properly. So for H3PO3, you just need to be a little bit careful here. Yeah, and you also need to take note that the OH sigma bonds are not being shown. Okay, so if you do a quick count, you should get a total of 6 sigma and 1 pi bond. Okay, so the pi bond is between phosphorus and oxygen. Yeah, so whenever you have a double bond, that will be 1 sigma 1 pi. When you have a triple bond, that will be 1 sigma and 2 pi. Okay, and if you need to review your chemical bonding, you might wish to know that for it to form a pi bond, it must have at least 1 unhybridized p orbitals. Yeah, but of course, this is not being asked for in the question. For part 3, you are required to describe in terms of orbital overlap how the pH bond in H3PO3 arises. Include a labeled diagram in your answer. Okay, so total credit is 2. So obviously here you should kind of be aware that the description will carry 1 mark, the labeled diagram will carry another mark. Okay, so for description wise, I think based on what you are given, you know that phosphorus is sp3 hybridized. Yep, so in your answer, you should have a sp3 hybrid orbital that looks like this. Okay, so this will be a sp3 hybrid orbital. Remember that you need to label it. So this is sp3 of phosphorus. Okay, so just remember to label your hybrid orbitals. And then overlaps with H. And H utilizes 1s. And remember that for 1s is principal quantum number 1. So definitely in terms of size, it cannot be bigger than the hybrid orbital. So a lot of you actually drew a relatively huge circle. Okay, so just make sure that your circle is quite small. Okay, don't need to be too small, but something like that will do. Yeah, so you just label it as 1s of hydrogen. Okay, yep. So this is a label diagram you are required to draw. What about the description? You are supposed to describe them as an head-on overlap. Okay, so this is very important because this showcases your understanding of the formation of a sigma bond. Okay, so this is a head-on overlap, or I think in some textbook they wrote it as end-on overlap. Okay, so any correct description will give you the credit. Of course, if you give description beyond head-on and end-on, then on our end, we'll have to check whether these terms are legitimate or whether they have been used before. Okay, so these are the 2 most common terms, head-on and end-on overlap. Okay, so just make sure that you use them in your description. Okay, part 4. For part 4, you were told that the first acid dissociation constant of H3PO4 is 2.1. Okay, so maybe it will help if we draw in the conjugate base of H3PO4. Okay, so that might be a little bit easier. Okay, so it will look like this. So there's a phosphorus here, double bond O, and then HO, and then O minus. Okay, and then we're going to join the conjugate base of H3PO3. Okay, so it will look something like this. OH, phosphorus, and then a H here. Again, O minus, and a double bond O. Okay, so you were told that maybe I'll write it in red. Okay, so the pKa1 is 2.1, pKa1 of H3PO3 is 1.3. Okay, so obviously from the pK value, the first thing you can actually discuss is that H3PO3 is a stronger acid as compared to H3PO4. And being a stronger acid, you should be able to conclude that the conjugate base is more stabilized. So this is more stabilized. Okay, so yeah, you can include some of these points in your answer. And then what is crucial in the question, if you read it right, is that you are required to suggest whether the OH group in H3PO4 and H3PO3, whether they are electron donating in nature or electron withdrawing in nature. Okay, you're supposed to comment on them. Yeah, so remember that we have discussed a little bit about this in our lectures on phenol, as well as carboxylic acid, as well as acid-base equilibrium. Okay, so the main thing we discussed was that for OH group, depending on the atom is bonded to, or depending on the hybridization state, okay, of the center is bonded to, it can either be overall donating or overall withdrawing, okay, or what we call sigma donating, or pi donating but sigma withdrawing. Sorry, it's not sigma donating but sigma withdrawing, okay, or sigma withdrawing but pi donating. Yeah, so it really depends on the group that it is bonded to. Okay, so over here it is very difficult if we do not give you any clue to actually decide on whether is it donating or withdrawing. Yeah, I agree that it's not easy. However, we gave you the clue that the conjugate base of H3PO3 is more stable. How do you know? Because we gave you the pKa value. Okay, so from the pK value, you should be able to tell me or share with the examiner that why is it that the conjugate base of H3PO3 is more stabilized? It is more stabilized because the lone pairs of electrons over here is able to delocalize to a greater extent, okay, to the PO pi system. Okay, so remember that delocalization is always through the pi effect, okay, or the overlap of the p orbital because they are of similar symmetry. Okay, so the conjugate base of H3PO3 being more stable, we can conclude that the lone pairs of electrons delocalize to a greater extent as compared to that in the conjugate base of H3PO4. Then why is it that why is this lone pair so special? Okay, I shouldn't circle the whole thing. I should just circle this. Or rather not circle this, but I should just highlight in purple. Okay, so why is this lone pair being able to delocalize to a greater extent? That is because it only has one OH group over here. So there's one OH group. Okay, but for the case of H2PO4 minus, there's two OH group. So the presence of two OH group, okay, will result in the lone pairs of electrons on O minus to delocalize to a smaller extent. Why is that the case? Because the OH group is electron donating. Yeah, so because one side already donates, so the lone pairs of electrons cannot delocalize as much as it wants to. I mean, very colloquially, that's the way I will put it in a colloquial way, but of course, in chemistry, you don't write it that way. Okay, yep, so in that case, our conclusion is that the OH group is donating, electron donating, and that results in the lone pairs of electrons on the O minus here delocalized to a smaller extent as compared to this lone pairs of electrons, which is being highlighted in purple. Yep. So I have to say that here we are testing you on this particular learning objective that appears in your syllabus. You can look it up. It's 11.1 C1 and C2. Yeah, so these are introductory organic chemistry learning objectives when we test you, or where the students need to understand the terms of delocalization, electron donating, electron withdrawing group. I know that when you were learning introductory organic chem, not a lot of attention was being placed on them because most of the time we will highlight to the students that you will learn more of them in JC2. Yeah, and usually you will get better at them after you studied acid-base equilibrium and after you have discussed carboxylic acids and phenol and alcohols, etc. Okay, yeah. So and then after that, you might be thinking, hey, this question is not even on organic chemistry. Yeah, but it is still applicable because it is based on the students' appreciation and understanding of this idea of donating, withdrawing, delocalization, stabilization, etc. Okay, so it is still perfectly legitimate to test the students. So do be very careful when you are handling or when you're going through your A-level exams, because sometimes they may test you some things which you thought is not really relevant in the syllabus, but it's actually quite relevant on the whole. Yep. Okay, so that is A part 4. Gonna move on to the energetics question. Yeah, this is quite a challenging energetics questions on hindsight. Okay, why is that the case? Because it is not your usual fare where you're supposed to just draw a Born-Haber cycle and then you're done with it. Okay, it's not very straightforward. Why is it not very straightforward? Okay, so to begin with, you need to look at the information given to you on the enthalpy changes or the energetics term being given to you. Okay, so first of all, right, what you are required to do is to calculate the enthalpy change of formation of H, or rather of PO form 3 minus gaseous phosphate. Okay, to help you to solve this question, the definition has been written out for you. Okay, so please make use of this definition in order for you or in order to help you to solve this question. And remember that when you are drawing out your cycle, okay, the charge must balance. Quite a number of you we noticed, right, did not balance the charge. Okay, so that resulted in some credits being taken away from you. Okay, yeah. So next, we're just going to look at a table. Okay, so for table 3.1, you are given 5 enthalpy changes, okay, or 5 energetics term. So you are given enthalpy change of solution of the nickel phosphate. Okay, if I were you, I will actually do this first because this is what I'm given first. Yeah, but of course, some of you might stick to doing what you are required to do, which is to put this at the beginning, but it can be a little bit difficult. So my suggestion is, since you are already given the enthalpy change of solution, then you can just make use of it and then maybe write out the first equation and then leave the details to the rest. Okay. Of course, quite a number of you chose to start from lattice energy of nickel phosphate. That's fine also. It doesn't matter how you start. Okay, in this case, actually all road leads to Rome. So you can get the correct answer no matter how you start off your working. Okay, so first of all, as mentioned, right, you have to do it step by step. So for example, I need to write out my definition. So make sure that I have the correct number of ions. So nickel 2 phosphate is Ni3PO42 solids. Okay, so over here I'm defining the enthalpy change of solution. Okay, so make sure you write in your state symbols as well. So that will be 3Ni 2 plus aqueous, okay, plus 2PO4 3 minus aqueous. Okay, so make sure you work it through religiously like that. Okay, it's really easier. Okay, yeah. Some of you try to link the nickel phosphate solid, okay, to an enthalpy change of formation term. Okay, so maybe let me just write it out first, then you know what I'm talking about. Okay, so some of you try to have an enthalpy change of formation like 3Ni solids plus 2P solids plus 4O2 gas. You try to have an enthalpy change of formation term, but you realize that this information is not given to you. If it's not given to you, then there's no way you can go about solving it because we're not asking you to solve for the enthalpy change of formation of nickel 2 phosphate. Do you realize that? Yeah, we are actually asking you to solve for us the enthalpy change of formation of gaseous phosphate anion. Yeah, so if you are trying to go around the problem by trying to solve this, then you are making your life extremely difficult because this information is not given to you. Yeah, and then you try to reinvent some terms. For example, you might do some bond breaking, bond forming, but you're not given a lot of these information. Yeah, so it's actually making our life very difficult. Then why not just use the enthalpy change given to us? Yeah, so the one that is highly possible in our case here is not this, okay, but rather lattice energy, right? Correct? Because remember that there are two ways to link up enthalpy. There are two ways to link up nickel to phosphate solids. One way is through the solution enthalpy, which I have already written in blue. Another way is through lattice energy. Then why not I just write in? I just write out the lattice energy definitions. Yeah. So again, if you are not sure, just write out first. You can always erase it later. Okay. And just make sure that your charge is balanced. Okay. So this is extremely important. Okay. So this is gaseous. Okay. It's negative 12,300. Okay. Yep. So this is, yeah. So now my job is try to link up the two, the part of the aqueous ions and then the parts on the gaseous ions. And then you notice that this term appears already. So if it appears already, what we need to do is try to push towards it, right? Correct? Yeah. So that's what you learn in JC1. Okay. So now since this term already appear, then why not I just write out the definitions? So I'm going to just arrow it. Maybe I'll write it in purple. Okay. So if I let the enthalpy change of formation of this, let's say I let it be x. Okay. So in this case, it's 2x, right? It's 2x. Okay. Yep. So I'm just going to write out the whole thing. Okay. So I'm just going to keep my nickel 2 plus impact. So 2 plus gaseous. Okay. Then plus 2p solid plus 4O2 gas plus 6 electrons. Yes. Okay. Make sure that your charge is balanced. A lot of you the charge not balanced. Okay. A lot of you the charge not balanced because you chose to do something else first. Okay, you know what I'm talking about. Okay, so guys, just go and check your scripts properly. Okay, and I think because I highlighted yellow, it's quite obvious what is the next thing you should do. You should be doing first and second ionization energy of gaseous nickel atom. Correct. So I'm just going to flip over the data booklet. So make sure the 3 is there. Okay, 3 equivalents. Okay, first IE is 736. This is the only one not given, huh? So you need to look up from your data booklet. Plus 1750. Okay. Okay, remember that you must have a 3 here. So of course from here, what I'm gonna have is simply 3Ni gaseous plus 2p. Okay, so plus 2p. Sorry, my pen is not really working very well. 2p solid plus 4O2 gaseous. Okay, right. Right. So then next, I'm just trying to link up these two portions. Okay. Then I need to check out what information am I lacking or what have I not used. Okay, so I have used this. I have used the lattice energy. Have I used the enthalpy change of atomization for nickel? Nope, not yet, because my nickel is still in the gaseous phase over here. Okay, so maybe I'll just highlight this little thing so that you know that this is where we are looking at first and second IE. Okay, so yeah, so let me try to create another not create but submit another enthalpy change term. That is the atomization for solid nickel to produce gaseous nickel. So that's 431 and 3 equivalent. So 3 times 431. Okay, so here I'm going to have 3Ni solids. Okay, plus 2p solids plus 4O2 gas. Okay, so I think right now we are very close to the answer already. Why is that the case? Because the next thing we're going to do is simply to put in the enthalpy change of formation of nickel 2 plus aqueous. So that's negative 54 kilojoules per mole. Okay, so this will automatically create or produce the electrons I needed to close up my definition for the enthalpy change of formation of phosphate aqueous. Okay, so over here I'm just going to add negative 54 times 3. Okay, so I'm just going to write in green over here, so that will be 3Ni 2 plus, okay, sorry, 3Ni, okay, so Ni2 plus aqueous plus 6 electrons, okay, plus 2p solids plus 4O2 gas. Okay, and then I'm going to close up everything. That will be negative 1277 multiplied by 2 because 2 equivalent of phosphate is being formed. Okay, so that's it. Yeah, so I get a completed cycle and I avoided the trap. Okay, I didn't avoid it. What I did was I put in the enthalpy change of formation earlier on, and then after that I reminded myself that I'm not given that piece of information, and then if I'm going to force my way through, I will need some information of bond energy which I do not have. Okay, yep. So from here you can apply Hess law. So apply Hess's law, okay, to get x equals to 327 kilojoules per mole. Okay, just apply it accordingly. I don't think you guys need me to teach you how to apply it, but maybe just to go through this concept very quickly. Yeah, so I need to go from here upwards, right? Okay, I need to go from here to here, right? Okay, so if I cannot go directly, I will need to go the other way around like this. Okay, so if I go the other way around, first I need to just check, am I going against the flow of the arrow or going in the same direction as the arrow? If I'm going against the flow of the arrow, I need to multiply everything by -1. If I'm going in the same direction, then I'll just put that value in. Okay, so that's about it, and you will get plus 327 kilojoules per mole. Okay, right. Okay, so the next thing we're going to look at is part C. Okay, so part C, you notice that there is an equilibrium being established between nickel and carbon monoxide. So originally, this question was sort of developed into a KP calculation, but of course, later on, we decided to just morph it into more of like a question testing you on recall learning objective like physical properties of nickel, etc. But surprisingly, it wasn't very well done. Okay, yeah. So just make sure that the first thing you need to look at when you are working on such problem is that we are testing you on physical properties. Okay, not chemical properties. So we are not asking you to tell me that nickel has variable oxidation state, or nickel can behave as a catalyst, etc. Okay, so we are looking at chemical property. Sorry, we are looking at physical properties such as melting point, density. Okay, they are directly from the notes. Okay, so the learning objective, if you wish to know, is actually 13D. It's under transition metal, where you need to understand that transition metal usually have higher melting points and higher density as compared to main group metals such as calcium. Okay, so in our case here, I'm just going to verbalize the answer a little bit. So for nickel's case, I'm expecting the melting point to be higher than that of calcium. Why is that the case? Because as compared to calcium, where it contributes only the 2 electrons from its 4s orbital, for nickel, it has the potential of incorporating electrons from the 3d orbitals as part of the delocalized electrons. Okay, as part of the pool of the delocalized electrons. Of course, not every electrons goes into the pool of delocalized electrons. Those of you who have maybe studied a little bit on semiconductors, you will know that there's this thing called a conducting band. Okay, so not all the electrons go into there. Yeah, some of it go into it, but at least more than that of calcium. Yeah, so because of that, I'm going to expect the metallic bonding within nickel to be more extensive and stronger as compared to that in calcium. Yeah, so a very simple idea like that will give you the credit for the first physical property. The next physical property we are going to discuss here is actually the density of nickel. Okay, so nickel's transition metal tends to be denser as compared to main group. Okay, why is that the case? Yeah, because number one, we need to do a proxy here. So we need to know that density is actually, if we assume that the atoms are sphere, okay, so density is actually the mass per unit volume. Okay, but a proxy to volume here, if we assume that they are sphere, is the atomic radii or the ionic radii. Yeah, so that's for third pi cube. Okay, so therefore density is proportional. Okay, you can see that density is proportional to the mass over R cube. Yeah, but for our case here, if you are comparing directly with calcium, nickel's mass or atomic mass is definitely greater than that of calcium. Okay, and it has a smaller ionic radius as compared to that of calcium. Yeah, so in terms of density, for the atoms itself is already greater than that of calcium. And at the same time, because of its compactness, because of its small size, more atoms or more ions can be packed per unit volume. Okay, using a very simple idea about per unit volume. Okay, so if we have more of these kind of atoms or ions in that case can be packed in the solid state per unit volume. So you're going to expect nickel to be denser than that of calcium. Okay, so with that simple idea, you can get 2 credits relatively quickly. Okay, so next we are looking at C2, where you are required to explain why carbon monoxide is poisonous. Yeah, again, those of you who did bio, you can tell me about competitive inhibitor, etc. We don't need to go into details, but basically the main idea here is that carbon monoxide displaces oxygen from its binding with the iron 2 in hemoglobin. You do not even need to tell me that it's iron 2. Yeah, but for those of you, I mean, in the tutorials, I did mention to you that the irreversible binding is due to the fact that CO binds much stronger as compared to oxygen. And I did also go into details like CO is actually a pi acid ligand, etc. But we don't have to tell us here. So the main thing here is that CO, right, binds irreversibly, okay, to the iron 2 center in hemoglobin. Yeah, and because of that, the oxygen transport around the body is now being inhibited. So you do not have enough oxygen to be transported around the body. So because of that, then it's going to cause cell death, tissue death, etc. So again, we don't need you to go into details. Again, it's 2 marks. So main thing here, of course, you really need to highlight to us that it's the irreversible binding of CO with the iron 2 in hemoglobin. And then this is actually a ligand exchange reaction, okay, and displacement of oxygen. Remember that. And then, of course, what happens after that? Oxygen cannot be transported around the body, and that leads to suffocation, self-death, etc. Yeah, as much as I have to say that quite a number of you are quite good in application question, but recall question is also very important in A-level exams. So make sure that you also score well in these recall questions. Okay. Next, we look at part D. Okay, so for part D, we have what we call a catalytic cycle. Okay, so it may seem a bit confusing at the start, but once you understand it, you realize that the catalytic cycle is actually quite an elegant way of representing chemical reaction. Okay, so what do all these arrow in and out means? So it has been explained to you, okay, below figure 3.1. Okay, so over here, maybe I'll just highlight in yellow. Okay, so the 5 steps can be written as 5 separate equations. So step 1 can be written as NiL3 plus HCN to give you A. Okay, so basically for catalytic cycle, right, we are summarizing what happens in separate equations, but we make it as a cycle because it's easier to read. Okay, so basically NiL3 plus HCN, you get this. Okay, then for step 2, what you have is A kick up L to give B. So that's about it. Okay, and then of course, what about step 3? Step 3 will be B, and this particular compound, cyano compound, reacts to give you C. And then what happens in step 4? Basically, there's some rearrangement going on, and then C gives D. Okay, and then in the last step, B, okay, combine with L, and then in the process, NiL3 is regenerated, and at the same time, adiponitrile is being expelled. So that is actually the synthesis of this important precursor to nylon 6,6. Okay, so if you try to write out everything, if you try to write out everything, right, you should be able to cancel most of the things away. And then at the end of the day, you will be able to get this. Okay, so basically just this unknown, okay, plus HCN, and then you get your adiponitrile. Okay, so that's NC, okay, like this. Yeah, so this will be the final answer you get. Okay, then some of you might be wondering, is it possible to just look at the diagram and then to see for the answer? Yes, you can actually do that, and that is the purpose of the catalytic cycle. Yeah, you can just look at the cycle one round, right? Okay, and then do the cancellation accordingly. So let me erase this to help you to visualize it a little bit. Okay, so you'll notice that the only thing that's being introduced, right, is HCN and this compound. Okay, you notice that NiL3, right, is being regenerated. So NiL3 shouldn't appear in the answer. Agree? Yeah. And then you notice that L is being kicked out here, but L is being introduced here. So L also shouldn't be in your answer. Okay, and then what is given out at the end of the day? Adiponitrile. Yeah, so that's it. Because whatever that's produced in the cycle is being consumed in the next step. Agree? You see, A is produced in step 1, but A is being consumed in, or rather, A reacted away to give B. And then B is being B reacted away to give C, and C reacted away to give D, or rather C rearranged to give D, and then D reacted away to give adiponitrile and NiO3. So if you can see that straight away, then yeah, the balance equation can be written out quite easily. Okay, yeah. Then for D part 2, you were already told that L is electrically neutral. Okay, that means that the phosphine ligand do not have a charge. Okay, so it's a neutral ligand. Yeah, so no charge means no charge, neutral, right? Just like CO. Okay, and then you were also told that the other two ligands, hydride and cyanide. Hydride, most of you are aware that is H minus. Cyanide, Cn minus. Agree? So if you do a quick count, the nickel center in A has an oxidation state of +2. Correct? Because the three phosphine ligand, namely L here, do not have a charge. So Cn is -1, H is -1, so +2. Okay, but what about what happens after that? Okay, so you were told that step 1 is known as oxidative addition. Okay, so step 1 is over here. Okay, so I jump start a little bit. Okay, so I'm talking about A, right? So the catalyst over here, right? Ni, the charge is, or rather oxidation state is 0. There's no charge, right? Because L is a neutral ligand. And then in step 1, the nickel center become +2. Yeah, so it's an oxidation because the nickel is being oxidized from 0 to +2. As simple as that. So all you need to tell me is that it is an oxidation because nickel is being oxidized from 0 to +2. And why is it called addition? It is called addition because it seems that the HCN is added across the nickel. Yeah, so it's like a addition reaction, right? Yeah, so that's all you need to say. Or you can say that HCN become two ligand, hydride and cyanide, respectively, and bond to the nickel center. That's why it's an addition. Yeah, and then actually, if you look at the original question, we also wanted to ask you why is it that step 5 is known as reductive elimination. Okay, so again, the opposite of oxidative addition is reductive elimination. Yeah, you can do that quite easily because the nickel center here is +2. Okay, and the nickel in the catalyst is 0. So it's called reductive elimination because nickel is being reduced from +2 to 0. And then it's what is being eliminated? Adiponitrile. So that's why it's called reductive elimination. Okay, you are actually asked to apply that in part 3, although you were not told the term reductive elimination, because you were told that intermediate C can undergo a similar reaction as that in step 5 to give NiL3 and E. Yeah, so from the pattern here, you notice that for reductive elimination to take place, right? I'm going to highlight is between this carbon and this carbon. Okay, so the carbon directly bonded to the nickel will interact directly with the cyanide. Okay, so if you go through the same logic, then you'll know that the product is between these two. Okay, and because of that, you can quite easily draw in compound E, which is like this. Okay, so I hope it's not too daunting after the review. All right, next, I'm going to finish this off very quickly by looking at part E, which is a kinetics question. Okay, so you were told that the overall reaction in figure 3.1 is shown with this particular rate equation. You notice that the rate equation includes the ligand. Some of you might be wondering, why does it include the ligand? Okay, I do not want to go into the details because the actual kinetic studies was performed and it's a very complicated reaction because it involved just too many reagents. Okay, but yes, there's nothing wrong with the question. Okay, the rate equation involved the ligands. Okay, and then you were told that a large excess of HCN and alkenes are being used, so the rate law is simplified to this. Okay, some of you were wondering, how can I get from the rate to this? If you recall from mathematics or recall from what you have learned maybe in physics, if you don't do physics, then maybe you can just do the mathematics, just take logarithm to the base 10 on both sides, and then you end up with this. Once you end up with this, you realize that the gradient, okay, is actually the order of the reaction, correct? Because it's here. Yeah, so if I plot log rates, okay, which is what I'm doing here, okay, I'm going to highlight in pink. Okay, so if you plot log rate against log concentration of L, right, this is the graph I'm getting. Okay, please do not misunderstand that a straight line means first order kinetics. There's no such thing. Okay, because it depends on what you're plotting. Okay, are you plotting log rate against log L, or you're plotting against rate against concentration, or you're plotting concentration against time? It's very different. Okay, so do not assume that straight line means zero order, first order. No such thing. Okay, please go and do the mathematics, and then I think the answer will be quite clear cut. Okay, so for the first part, it's asking you for your appreciation of pseudo-order reaction. So explain why the rate law can be simplified to that in the kinetic studies. Yeah, so again, because I have a large excess of the two, right, HCN and alkenes, so you expect their concentration to change minimally in the course of reaction, or you can say that their concentration is taken to be constant in the course of reaction. Okay, because maybe when all the L's are being consumed, or all the reactants are being consumed, right? Their concentration, the concentration of HCN and alkene did not change appreciably. Okay, so the main idea here is to focus on the fact that that there is excess HCN and alkene, and their concentration do not change appreciably in the course of the reaction. So remember that. Okay, and then for part 2, figure 3.2, you're supposed to use it to determine the order reaction. Yeah, so basically, yes, you can take any points. Okay, as far apart as possible, preferably. Okay, any point. You perform the mathematics. Okay, find the gradient. You should get -2. And please, when you get -2, don't change your answer. -2 is -2. Please believe yourself. Yes. So the order of reaction, as I mentioned before in the kinetics lecture, right? That was last year. It need not be 0, 1, or 2. It can be fraction. It can be negative number. So what is the significance of a -2 kinetics? So -2 here means that when you double, okay, when you double the concentration of L, the rates of the reaction will become a quarter of its original value. Okay, or you can say that it will be reduced by a factor of 4, but I think this is quite hard to express, although we ask you what factor will the rate change. Okay, yeah, so the easiest way to explain or to answer this question is just to say that when L doubles, the rates will be reduced to a quarter of its original value. Please do not say things like it reduced by 75%, or the rate become times 1/4 or times 3. You know, it's very difficult to imagine sometimes. Okay, so just write out properly in English. Okay, reduced to a quarter of its original value. I think that will be perfect answer. Okay, so this is the end of the review to question 3. We hope you find it useful in your revision. Okay, and all the best to your A-level preparation.